simplify n minus 13 factorial over n minus 15 factorial. So first we decide which number is bigger. So you start with a number n and you subtract 13 compared to starting with a number n and subtracting 15. Subtracting 13 is going to give you a bigger number, right? Subtracting 15 will give you a smaller number than if you subtract 13. So the bigger number is on top. So I'm going to start by writing out the factorial for n minus 13. So it's n minus 13 times n minus 14, right, one smaller, times n minus 15 factorial. And then the bottom is n minus 15 factorial. Those cancel, and you just are left with n minus 13 times n minus 14. Okay, this one looks a little more complicated. First thing I should do is simplify the denominator. I have all this stuff in parentheses that's factorialed. So I'm going to write this as 2n minus 5 factorial over, that's 2n plus 2, then minus 5. So I'm distributing the 2, combining like terms, and I get 2n minus 3 factorial. And then both the numerator and the denominator are being cubed, so I can just cube the entire fraction. All right, so now I'm just going to work on the inside piece of this, ignoring the cubing for now. I have to decide which is larger, 2n and subtract 3, or 2n then subtract 5. So subtracting 3 should give me the larger factorial. So my numerator I'm just going to write as 2n minus 5 factorial. It's the smaller of the two factorials, so we just write that as is. And then 2n minus 3, that's bigger, so that one I'm going to start writing out. So 2n minus 3 times 2n minus 4, and then I've hit the 2n minus 5 factorial. So my factorials cancel. And remember, all this is cubed. So my answer is 1 over 2n minus 3 times 2n minus 4. And then I'm going to cube the numerator and the denominator. 1 cubed just stays 1, and then I can cube each of these terms. Shouldn't have said terms. I can cube each of those factors. There are two basic ways a sequence can be defined, explicitly and recursively. So here is an example of an explicitly defined function sequence, an explicitly defined sequence. So I want to list the first 5 terms of this sequence. So a sub 1, I'm going to replace all the n's with 1s. So I have 1 plus negative 1 to the 1 times 1. So negative 1 to the first is negative 1. Negative 1 times 1 is negative 1. 1 plus negative 1 is 0. A sub 2, that's going to be 1 plus negative 1 squared times 2. So negative 1 squared is 1, times 2 is 2, plus 1 is 3. A sub 3, that's 1 plus a negative 1 cubed times 3. Negative 1 cubed is negative 1. Negative 1 times 3 is negative 3, plus 1 is negative 2. A sub 4 is 1 plus negative 1 to the 4th times 4. So that is 4 plus 1 is 5. And finally, a sub 5 is 1 plus negative 1 to the 5th times 5. So that's negative 5 plus 1 is negative 4. Okay, we can also define sequences recursively. So that means that there's an equation that relates the nth term to the previous terms, and we also need to know how the sequence starts. So these are some recursively defined sequences. I'm being told that the first term of the sequence is 1, And then the nth term, any term in general, is the term before it plus 2 to the n for when n is bigger than 1. So I know a1 is 1, so that was given. And then a2, the second term, is the term before it, a sub n minus 1, so a1 plus 2 to the n, and n is 2 in this case. So that comes out to, oops, 2 to the 2. There we go. So a1 is 1 plus 4 is 5. a3 is going to be equal to the term before it, a2 plus 2 cubed. So a2 is 5, so that's 5 plus 8, which is 13. And a4 is a3 plus 2 to the 4th. a3 is 13. 2 to the 4th is 16, so that is 29. And yeah, I just needed to find the first 4 terms. Okay, my next one, a1 is 1, so that's given. a2 is going to be 2 times the previous number in the list. So 2 times 1, which is 2. a3 is 2 times the previous number in the list, which is 2, 4. And a4 is 2 times the previous number in the list, which was 4, so 8. Okay, we want to figure out an explicit formula for each of these sequences. These can be tough. They take some practice, and sometimes they take a trick that sometimes you just see or don't see. So for this first one, 1, 3, 7, 15, the first thing I see is that this is really close to a sequence that I know well. So if I add 1 to every single term in this sequence, I get 2, 4, 8, 16, 32, 64, and those are doubling. Those are the powers of 2. So a sub n is 2 to the n, but then I need to subtract 1, right? Because this blue sequence is 2 to the n, but the sequence I was asked about is 1 smaller. So 2 to the n minus 1. Okay, so this next one, the hint or the clue that you might zero in on is the 9 and the 25. But those are denominators that are perfect squares. So I'm going to rewrite the sequence. This becomes 5. This is 5 over 9. I'm going to skip that one in the middle there, and 7 over 25. And 3 over 8 could be rewritten as 6 over 16. And now I'm like, oh, that was a good clue. Now I have 3 denominators that are all perfect squares. Can I rewrite the 1 as a denominator with a perfect square? So 9 is 3 squared, 16 is 4 squared, 25 is 5 squared. So before the 3 squared, I probably want 2 squared. So I'm rewriting the 1 as 4 over 4. And then if I'm following the pattern, the previous number in the list would have a denominator of 1. So I can rewrite 3 as 3 over 1. And now I can try to use the pattern I've discovered to write a formula for a sub n. So my denominators are just n squareds, right? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And my numerators are 2 larger than the number I'm squaring. So n plus 2. Determine whether each sequence is convergent or divergent. Begin by writing the first 4 terms of each sequence. So a1, this is 5 plus negative 1 to the first, which is 4. a2 is 5 plus negative 1 squared, which is 6. a3 is 5 plus negative 1 cubed, which is 4. And a 4 is 5 plus negative 1 to the fourth, which is 6. So this sequence is just bouncing between 4 and 6 forever. So this diverges. It does not approach a single value, one single limit, which means it does not converge, so it diverges. Okay, so for b, I have the first term is 4 plus the cosine of pi, which is negative 1. So 4 plus negative 1 is 3. A2 is 4 plus the cosine of 2 pi is 1. 1 over n, which is 2. So this is 4.5. And then a3 is 4 plus the cosine of 3 pi is negative 1, so negative 1/3. 4 minus a third is 3 2/3. And then a 4 is 4 plus the cosine of 4 pi is 1 over 4, so that's 4 1/4. So these values do seem to be approaching 4, and that is because the fractions are getting smaller. So that one was 1, then a half, then a third, then a fourth. The next one's going to be a fifth, then a sixth, then a seventh. So they're getting smaller and smaller and smaller. Some are positive and some are negative, but overall, they are approaching 0. So a sub n is approaching 4 plus 0. So a sub n is approaching 4. So that is what it converges to. Okay, female bees develop from fertilized larvae, which means that female bees have a male and a female parent, whereas male bees develop from unfertilized larvae. So male bees have only one parent, a female bee. The diagram below traces the family tree of a male bee back. So this is an upside down family tree. So the current generation, we have a male bee. His parent was a female bee, because males come from only one female. And then that female bee had two parents, a male and a female. So males always have just a female parent. Female bees always have two parents, a male and a female. So we're going to keep working our way back here. So females develop from a male and a female. A male develops from just a female. And female, a male, and a female. So that makes a total of 5 bees in that generation. So continue working our way back. This male bee came from a female bee. This female bee was made by a male and a female. Male, female, male bee from just a female, and then this female bee came from a male and a female, and that makes a total of 1, 2, 3, 4, 5, 6, 7, 8 bees. All right, so that means that in generation 7, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bees. Here we have one more generation to go. So male came from a female, female, male, female. Okay, that means that in this generation we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 bees. Okay, we want to find a pattern to the numbers in the right-hand column. Write your pattern for finding the next number in plain English. So let's go back and look at the column. So the pattern that you should discover is that each number in the list is the sum of the two numbers before it. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34 would be the next number in the list. So each number in the list is the sum of the two previous numbers. So generation 9 and 10. So we went as far as generation 7. Oh, we went generation 8. Okay, so generation 9 was 34. So generation 8 was 21. And we said generation 9 would be 34. So generation 10 would be 21 plus 34, 55. Okay, try to translate your answer from part D into a recursively defined formula. Use Fn instead of Gn to represent the general term of the sequence. So the nth number in the list is the sum of the previous two. So the one right before the nth is the n minus first, and the one before that is the n minus second. And then you also need to define the starting values, F1 and F2. So this sequence is called the Fibonacci sequence, named after Leonardo of Pisa, nicknamed Fibonacci. He did not invent the sequence, but it appeared in a text that became associated with him. So compute the first 20 terms of the Fibonacci sequence using the recursive definition. So I know 1 and 1, then I've got 2, 3, 5, 8, 13, 21, 34, 55, 89. Okay, I finished the list. 55 and 89 is 144. 89 and 144 is 233. 144 and 233 is 377, etc. Okay, so I've got the first 16 Fibonacci numbers here. Next page I have up through 17 through 20. Do the Fibonacci sequence numbers converge or diverge? They definitely diverge. They are just getting bigger and bigger. It looks like f sub n approaches infinity. Okay, the sequence of Fibonacci quotients is defined as a sub n is f sub n plus 1 divided by f sub n. We want to compute the last 4 of the first 20 Fibonacci quotients, the ones that are on this page, and put our answers in the right-hand column. We want 7 digits. So the 17th Fibonacci number divided by the 16th. So I want 1597 divided by the 16th Fibonacci number, which was 987, which is 1.6180345 if I round to 7 digits. Okay, 18th over the 17th, 2584 divided by 1597, and I get 1.6180338. The 19th divided by the 18th. And we get 1.6180341. And one more here, the 20th divided by the 19th. 6765 divided by 4181. And I get 1.61803339. Does the sequence of Fibonacci quotients appear to converge or diverge? It definitely isn't growing without bound. And it does seem to be bouncing up and down a little bit, but it's kind of going like up and down and up and down and up and down, and it does seem to be converging on a single value that is somewhere in the 1.61803 range. And that's it.